all things fall at the same rate, regardless of how much they weigh or what they're made out of. That says something about how gravity works. And in fact, scientists have elevated this to a principle called the Equivalence Principle, which says that gravity is basically indistinguishable from uniform acceleration, at least if you confine yourself to a small region of space, such as this room. Over a larger region, there would be tides, but that's another story. So the Equivalence Principle implies that if aliens kidnapped you and put you on a rocket ship with no windows, took you far from Earth's gravitational field, as long as they accelerated the rocket at 9.8 meters per second squared, you would feel the exact same effects. There's no experiment that you could do to determine that you were not actually in Earth's gravitational field. Now, why is that important? Who cares? Well, it actually allows us to figure out some things that we couldn't figure out any other way, such as answering the question, does light fall in a gravitational field? Light always travels at the speed of light, so it can't accelerate, and it's very impractical to do an experiment where we drop a piece of light and see if it falls. So the equivalence principle is actually a nice, useful tool for figuring this out. So instead of doing the experiment, we can imagine what would happen in an accelerating rocket ship, and then the same thing has to happen in a gravitational field. So what we have here is a rocket ship, and first imagine that it's at constant velocity and that there's a laser beam attached to the side of the wall, and that laser beam just is pointed straight across. Now, it doesn't matter what velocity this rocket travels at, as long as it's at constant velocity, the light has to travel straight across. Because if it were bent in any way, then that would violate the principle of relativity that says you can't tell what velocity you're traveling at as long as it's constant. So, if it's constant velocity, it travels straight across. Now, what happens if it accelerates? An easy way to see what happens is to imagine just one particle of light. So right there, it's just been emitted. Now imagine that there's an observer traveling along at the same velocity as the initial velocity of the rocket ship when the light is emitted. A short time later, the rocket ship it's accelerating, so it's now moving that way at some velocity relative to that observer. And remember, the observer traveling at constant velocity has to see the light travel straight. So the net effect of that is that when the light has made it halfway across the room, the observer who's traveling at constant velocity and sees the light traveling straight across space here has seen the ship accelerate upwards. And a short time even after that, the light continues traveling straight across as observed by that observer at constant velocity, but the ship has accelerated upward. So the light does not hit the wall opposite where the laser beam originated, which would be here, but hits the wall farther down. So the net effect of that, as seen by a person standing in the rocket ship, would be that instead of going straight across, this person sees the light bend down like that. So light does fall in a gravitational field because the accelerating rocket ship shows the light bending, and by the equivalence principle, that's the same as being in a gravitational field. And in fact, experiments have confirmed this. And one other thing you can get from the equivalence principle is gravitational redshift. So now imagine the light pointed down there, and there's your person. Now if this ship is traveling at constant velocity, the wavelength of light that comes out of here is going to be the same wavelength of light that this person measures by the time the light gets down here. But if this ship is accelerating, what happens is the observer here is accelerating towards the light, and so by the time he reaches the light, he's going to be at some velocity heading towards the light, which means that the light has to be blue shifted. So turning that around, according to the equivalence principle, if this were a gravitational field and you had the light at the top of a building shining down, a person at the bottom would see the light blue shifted. Now more commonly we talk about a gravitational redshift because more commonly we would have a source of light on the Earth and we would have someone far away in space observing it, and the gravitational field would result in a redshift of that light according to the distant observer. And the gravitational redshift actually leads you to the conclusion that time runs slowly in a gravitational field, which was a previous video. So there's a very nice connection between the equivalence principle and the fact that gravity makes time run slowly.